review the string series one more time. The string series and then the wind column series with penny whistle. Fundamental. First overtone. Second overtone. Third overtone. Fourth overtone. Now I'm off with just a quick reminder about the fact that I can touch this thing at the nose and not get much change in the waveform, but if I touch it at the antinode, I shut everything down. Now for this segment, I'm going to do something a little different with the string. Previously, we've been looking at strings that have been fixed at this end and fixed at the other end. For the wave medium, whenever that's waving, whether it's a string or a wind column, is the same at both ends. We get that all integer multiple series that you can hear with a penny whistle. Let's play the penny whistle again. What's characteristic of fixed at both ends is we get octaves. You get octaves because you have to have even multiples to get octaves. Octaves are always a doubling of the frequency. Okay? But something happens when it's not the same at both ends. So let's point this out. Fixed at this end of the string is free to vibrate. It's connected by a very light thread. So this end of the vibrating string is free to vibrate by itself. And we get a completely different series. Well, subtly different. Let's watch closely. Now here's the fundamental. It's fixed at this end, wiggling around like crazy at this end. I'm just going to tell you this rather than make you try to figure it out. This is only 1/4 of the full wavelength of the wave that could appear in here. Now I'm going to try to find the next resonant point, which is when this is wiggling around wildly again. So we should see a changing of the nodes and antinodes. Node, antinode. Here's the next resonant point. I'll bring a close-up here. I have a node here, and an antinode here, and an antinode here. What's interesting is the original frequency was around 7 hertz. Now I'm up around 21. 3 times. Now I'm going to get the next one. Now what's interesting here is I have node, 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 antinode, antinode, antinode. Same number. But in order to get this next resonant point, I had to go to 5 times. 1, 3, 5, do the math. 1, 3, 5, 7, 9. Only the odds. So the point of this segment is that when it's not the same at both ends, when one end is fixed and the other end is free to vibrate, I always have to have a node at one end and an antinode at the other. Changes the geometry. What it gives me now, and this is all you really need to know, is an odd series. No octave. So I'm going to go to the most simple wind column instrument that is out there, and this is a PVC didgeridoo. 1.5 inch wide, kind of long. This thing will produce notes that are the same at both ends, or fundamentals. First tube is the same at both ends, so I just give it a pop. Now, that would be fine with this sort of giant flute, and it would play all integer multiples. The catch is when you're going to play something like a brass one, like if I'm going to play this like a didgeridoo, I stop up one end with my face. And if you listen carefully to the note that I'm going to play, it's an octave lower. So for me to play a didgeridoo note, I'm going to play it an octave lower. I can only get odd multiples, and they have a strange sound. I'll show that again on the piano later, but for a strange sound indeed, because you have no octaves. This is the series that you get with this thing when it's capped at one end. clearly there were no repeated tones. Now this is another type of didgeridoo, if you will. It's much longer than the other one, and it's narrower. And I put a hose fitting on this end because it kind of hurts my lips to try to play it. And it has the same effect. It has an odd series, but because it's so long, I'm going to play farther up in the series. So the notes are closer together, but they still have a very strange sound to them. Not very useful as a musical instrument. All I'm going to do is put a mouthpiece in to this kind of a receiver that I've made with the pipe fitting. Now listen to what happens. But what happened was I added about 3.5 inches of tapered tubing. As we all know, a trumpet mouthpiece is about 1/8 of an inch across at the throat, flares out to about 1/4 of an inch. So that tapered tubing takes the odd series and kind of squishes it together. More on that later. If I put a funnel on the other end, it gets even better. It's a little funny to play, but it is a workable musical instrument. This is a PVC natural trumpet by using tapered tubing. That's the key. The didgeridoo was originally a cylinder. This was a cylinder, but by adding some taper to the tubing, it now acts like what we know and love as a trumpet. It fills in the gaps as the octaves. Part of the trickery, though, is it's not perfect. Because we're playing very high in the series, which is now a very close approximation to an all-integer multiple series. So natural trumpet, and it's basically just working with tapered tubing instead of cylinders. I know trumpet is often thought of as being a cylindrical bore instrument. That's sort of a misconception. It's only partially cylindrical. Conventional wisdom is about 2/3 cylindrical, 1/3 conical, but it wouldn't play if it didn't have about 1/3 conical tubing. When we have the string series or the flute series, the same series where the pipe is the same at both ends or the string is the same at both ends, we get an all-integer multiple series. It sounds like this. Fundamental, octave, fifth, another octave, third, fifth, flat 7, and then it starts to blur into a scale at the top. What's missing when you add, when you clap it at one end, when you close one end like you would with a trumpet or a saxophone, they work the same way. The octaves are missing. That's the series. No octaves. But what happens by adding the taper is you take this note, starts to collapse down. The notes start to collapse down and fill in the gaps of the missing octaves. The higher notes pull on down, the bottom notes pull on up, and what you've done is you've completely tricked the thing out by taking that spread out thing and squeezing it together to fill in the missing octaves and missing even multiples. And that's how it works. What's key to making this thing work is how well the taper is balanced. That's what makes a good trumpet play well, and a less expensive trumpet not play so well. Not all the notes in that bugle call series are perfectly in tune. That's fundamentally how a trumpet works. There's going to be more. We're going to talk about timbre and pedal tones in another segment.